All right, let me try to walk you through this. The percent composition of penny, this lab here, okay? What you're going to do, what we've done, we've already taken the penny and we've dropped it in 6 molar hydrochloric acid, okay? The idea here of using a penny that's younger than 1982 is the fact that in 82 the government decided that the penny was a solid copper penny was worth more than a penny. So they made little zinc patties, little zinc pellets, and coated them in copper and called them pennies, okay? Because zinc is much less expensive than copper. So what we're going to do with that is we're going to take that information and make a little single displacement lab out of it, okay? So what you'll do is you'll fill out this table, these data tables with your calculations. You've already got the mass of the penny intact with the zinc, right? And so what you'll do is, the hardest thing you'll have to do is get that penny out of the 6 molar acid because it was excess acid, so it's still very acidic. Get that out by diluting the acid down to the point where it's safe, then get the penny out of the beaker and then dry it off, okay? And when you get in your groups, I want you to try to figure out the best way to do that, and then if you have any questions about it, I'll give you my suggestions on how to do it. But the calculations is what I want you to do. This is a very simple reaction. However, you can make it useful in practicing some of these calculations. Okay? Any questions about what we're doing here? All right, so let's take a look at this first page. Okay, so number 1 here is asking you to write the equation for what we're doing. And what we're going to do, because we have this penny that looks like this, and this is, say this is copper, and then the inside here is zinc, and then it's coated with copper on the outside. So you got a layer of zinc in the middle. It's completely covered in copper. And when you look at this thing, you might see it looking like it's floating. It's because the acid goes inside the pennies where we scored it, and hydrogen's released, and so there's little hydrogen bubbles inside there making that little skin float. And there's not much copper in it. You're going to see that. You're going to calculate that. There's not much copper in it. So really what we have is a single displacement reaction, but it's a little bit unusual in that we are going to add copper and, right, zinc, and we're going to add it to hydrochloric acid, okay? Now, based on what you know about chemistry, what's going to happen here? And if you didn't know, you would look at page 286 and you'd look at your activity series, and it would tell you what? Go ahead. The zinc will displace the hydrogen in the acid. Zinc will displace hydrogen in water as well, right? I believe it's steam, but certainly in acid, okay? So we're going to end up with, in that case, when the hydrogen is forced to accept that electron, it no longer stays in water, and the hydrogen's diatomic, so it forms that 2-atom, that diatomic molecule, okay? And under these conditions, it's a gas, okay? So the hydrogen is going to bubble away. We're going to be left with zinc chloride. Zinc is a 2+ ion always. We don't say zinc 2 because it's only 2, okay? And so that means the formula for zinc chloride is what? Ms. Faust, what is it? Cl2, okay? Plus hydrogen, and to leave us some room here, I'll go ahead and put the copper here. What happens to the copper? Nothing. Nothing, right? The copper is unreactive, is so unreactive in this reaction, and nothing happens to it. We clean a little bit of the surface dirt and whatnot off of it, but that's it, okay? So, if we go back to our original data, we'll use some sample data here. And let's say, I have to go back here. What in the world? I need to go, sorry. Need to go back up here. And let's say for the sake of discussion, for practice here, and you don't want to write this in your lab, okay? You can put that equation in your lab sheet, but you don't want to put this data in your sheet. we're going to say we had 3 grams of penny, okay? And we'll say the mass at the end was, let's say 2.75, okay? So the amount, I'm sorry, we'll say 0.25, sorry. We'll say that the mass at the end, that's what you're going to go get the mass of now, is 0.25 grams. So that means that 2.75 grams of this thing was zinc, right? Okay, so we go back to our calculation there in number 3. I believe it's number 3 here. I hope it's there. There it is, okay? So our percent zinc then, okay, our percent zinc is going to be the mass of the zinc divided by the total mass times 100, which in our case was 2.75 over 3.00 times 100, which gives us what? Now again, don't write this on your lab sheet because this is just sample data, huh? 2.75. It says what I asked you just to write down a minute ago. It says right here, the mass of the zinc divided by the mass of the penny multiplied by 100. Okay? $91.6666666. So we round that to what? 91.67%. Okay? So the percent copper equals what? Well, it's going to be 100% minus 91.67 or 6666, yeah? Well, that's a good point. We should change that to 7, 91.7, okay? So we subtract the percentage here, and what do we get? 8 point, what is that, 8.333? Huh? So 8.33% copper, okay? 91.7% zinc, 8.33% copper, okay? So the moles of zinc, 2.75 grams of zinc multiplied by 1 mole of zinc per what? Off the table, 65.39. That's why I was trying to use 4 significant figures. And that gives us how many moles? The moles of copper. And this is really just a practice. It's just practice calculating moles. 8.33 grams of copper. And you multiply that by 1 mole of copper per 63.55 grams. Okay? And the moles of hydrochloric acid, you need to look at a new idea. This uppercase M here means molar, okay, or molarity. This is the way we quantify substances in solution, okay? And what this means is, what it stands for is moles per liter. Okay? Moles per liter. Now, we had 6 molar, right? We had 6 molar. We're going to play like we have an infinite number of significant figures here. We don't want to drop our significant figures to 2, but if we want to convert this to moles, what are we going to multiply by? No, you've got moles per liter. You have those two units. You want to get rid of the liter unit, so what are you going to multiply by? You're going to multiply by liters here. Yes? What was the volume that you put in there? 0.0200 liters. Yes? So liters cancel, and that gives you how many moles? Well, you can calculate it, right? So this is going to equal 0.12 moles of hydrogen chloride. How many moles did you come up with here? .042, right? 0.0421 moles of zinc. And here we had, what was it, 8.33? Nope. It's 0.833. It wasn't it? I don't know what in the world I'm doing there. That's the percentage. The mass is 0.25 grams of copper. It's 0.00393. Moles of copper. All right, any questions on this? I don't know, I'm not there yet. Okay, any questions on this? So we got 91% zinc, 8.33% copper. Those two together equal 100%. That's all a penny is, okay? Right? Now, what we're trying to do here, and this is another concept that we haven't talked about yet, is we're trying to make sure that we had plenty of acid to react with the moles of zinc that we have. Okay? If we didn't use enough acid, we wouldn't have enough, right? Okay? How many moles of zinc, how many moles of zinc does it require to react with how many moles of chlorine? Huh? It's a 1 to 2 ratio. You need twice as many moles of chlorine, or hydrogen chloride, same thing, right? Twice as many moles of chlorine as you have moles of zinc, and we do. Yes? Okay. Alright, so which metal is more reactive, and how do you know? And how do you know? Go ahead. What did you say, Mr. Adams? Because the copper did not react, and the zinc did, or went into solution, right? So the answer is zinc, right? Everybody understands that, Ms. Farnham? So when you get the lab quiz, which metal is more reactive, you know the answer, right? Okay. Any questions about this? All right. So now we're going to 8. All right. So in question 8, it says, where did the zinc, hydrogen, and chlorine ions go? You know, when we drop the zinc into the acid, it was pure zinc. There were no ions there. It was pure zinc. Had all its electrons. It was zinc atoms, right? Where's the zinc now? Huh? It's still there. Where is it? It's still in that beaker. It's in solution, right? The zinc went to zinc ions by losing 2 electrons, right? And it's in solution. Does everybody understand that? This is why we're doing this lab, okay, is to hopefully help you understand what's going on here. Does everybody understand that, Mr. Gradle? The zinc lost 2 electrons. Where'd the electrons go? Mr. Hurd? Mr. Butt? They went to the hydrogen, okay? So what happened here is the hydrogen ions gained the electrons and became hydrogen molecules, and where'd they go? Huh? I'm going to say bubbled away, okay? Everybody understand what I'm saying there? Because once the hydrogen gained that electron, it lost its charge. It's no longer a hydrogen ion. The water has no use for it, okay? It won't stay in solution. It's gone. Furthermore, it's a diatomic element, so the 2 hydrogens bond together and form that diatomic molecule. And at this temperature, 22 degrees Celsius, 1 atmosphere of pressure, it's a gas, right? And it bubbled out of the solution. How about the chlorine? I got a chlorine ion drawn there. It's a negative sign there, huh? It says, where did it go? I guess the answer is nowhere, right? Still in solution. Right? Now, I want you to look at that we just did, because this is where you need to step up and start taking the initiative to answer these questions on your own, okay? Any questions about any of these? Eight. Oh, I did skip 8, didn't I? 8 is the concept I said we need to go over that we haven't talked about. In every reaction, let's say we have 2 reactants. Every reaction where we have 2 reactants, you're going to run out of one reactant before the other, right? Because it's not like making cupcakes where you can measure, pretty accurately, right? And you can pretend like you use every single bit. But when we get down to the atom-to-atom ratio, you can't measure that precisely. So we will always run out of one reactant before the other. What happens when you run out of one of the reactants? For instance, if we run out of zinc or we run out of hydrogen chloride in this reaction right here, what happens? Stops. It ends. And what we say in chemistry is it limits the amount of product, right? Well, the reactant you run out of is called the limiting reactant. And that might be something good to write down, because a lot of times students make a mistake and they carelessly let themselves believe that the limiting reactant is the reactant you have the least amount of. Not necessarily so, okay? Particularly if you have a 2-to-1 or a 3-to-1 ratio of reactant to reactant, right, to produce product. So if you have a 3-to-1 ratio, you'll need 3 times more of one reactant than the other. In this case, you need twice as many moles of chlorine as you do zinc, right? That's why we made sure we used between 15 and 20 milliliters to make sure we had more than twice as many moles of chlorine as we do zinc, okay? So the limiting reactant in this reaction is what? Zinc. And that is the reactant. I'm going to say it fairly unscientifically. That is the reactant that I'm going to say used completely, okay? Okay? So zinc is the limiting reactant. Okay? Now, let's say that our percent error is 97.5%. I mean, our actual value is 97.5% zinc. What is our percent error in this reaction. And I recommend you do it by mass. If we had a perfect reaction, what mass of zinc would we have removed? 97.5% of 3 grams, right? 97.5% of that penny was zinc. How much zinc did we say we removed? Do you know? We said we removed 91.66%, 67%, right? So we know we're off. Now I don't want you to just compare percent to percent, I want you to compare mass to mass, right? So if we remove 97%, what would the mass have been? We'll take the actual percentage and we'll multiply it by the mass of the penny. And that's going to be our actual value. In this case, it equals what? 2.925, right? Is 2.925 grams, okay? This is 3. So our percent error then is going to be the actual value minus the experimental value, absolute value there, divided by the actual value, which is going to be 2.925 grams minus, what did we have? 2.75? Yes? Divided by 2.925 times 100. And that equals what? Anybody? I don't think so. Did you say 17? No. 5.98. 5.98% error. And you may do better than that, or you may not. I don't know. There should be very little error in this because we made sure we had excess hydrochloric acid. The pennies were scored correctly. The only error that I can see would be if you didn't score them completely. But we'll see. Okay. Any questions about how you do this? This is 8, 9, and 10. There's 1 through 6, 7. Okay? And then you realize this is sample data. Okay? All right, so we will go at it. You need to get in groups of 4, no more than 4. And you've got the pennies already